Congratulations! Andito na tayo sa final part ng series natin. Before, nakita natin ang overview ng Ising model kasama niyang kanyang pag-program, pag-code, kinami. Ngayon, let's analyze what we've learned. So, bale, yung previous videos palang foundation kasi sila yung bread and butter or foundation kasi bread and butter. Ngayon, meron na tayong icing on the cake. Hala, ano naman to? Ito ba talaga yung ginagawa namin kanina? Yes. So, sa 4 blocks na to, i-uncover natin ang mga underlying principles na naitakol ng previous videos. So, ngayon pa lang, nakikita mo na merong combination ng positive or negative J at small or big thermodynamic beta ang mga graphs. Nalilito pa rin ba? Kahit na last video na to, pwede pa din i-review kasi lahat ng component ng equations kanina ay nagko-contribute sa behavior ng graphs dito. So, remember how meron tayong lattice na na-initialize? So, andito yung lattice natin and it's a 2D array. Okay, so and from that 2D array, we're able to randomly fill it with +1 or -1 spins. So, those values, yung +1 and -1, it corresponds to upwards or downwards, like as you see here. So, take this one cell or site here, for example. Nagdetermine tayo ng rules para kung ano yung makonsider as neighboring spins ng site na ito. So, in this case, ginamit natin ang von Neumann neighborhood definition. So, basically, north, south, east, west lang, or up, down, left, right lang to the spin here. It doesn't include yung mga diagonals na magkatabi ng site na yan. So, I think na-mention din pala from previous videos na ang Hamiltonian dito ay yung summation ng interaction strength at yung spins, like yung index ng spins at each site. However, yung Hamiltonian na to ay para sa zero field Ising model lang. So, we will have to consider ang external magnetic field, which is why we will have to add an extra term later on, which you will see. So, the extra term na i-consider dapat natin ay yung para sa external magnetic field, H. Yan yung H. Kaya may extra term. Tapos, nasa-sum siya over all the spins of the lattice. Hence, ito talaga, yung buong equation na to, ang equation to determine the total energy ng system. So, yung first term ay over neighbors, tapos yung second term ay para sa lahat ng spins. So, now na kapag refresh na tayo sa equations needed, aalahanin natin ang purpose ng lattice. Kasi, that would explain its behavior. Pero, ito lang to. Yung point dito is, kailangan i-minimize yung energy for the system. So, makikita mo na ang total energy ay nakadepende sa alignment ng magkatabing spins. Kapag naka-align ang neighboring spins, bababa ang energy, di ba? Yung S sub I and S sub J ay mag-a-add sa total value. So, ngayon, we have to concern ourselves with delta E. So, we have yung final energy minus yung initial energy. So, ibig sabihin, kapag ang flip na yan ay magpapalower ng energy, then i-accept natin. Pero kung tataas yung energy, reject na ba agad? Not necessarily. May chance pa din na tanggapin natin depende sa temperature. Kanina, na-mention natin na if yung delta E is greater than 0, i-accept natin siya with probability P. So, ito na yung P na yan. Madedetermine mo siya by yung exponent, exponential of negative delta E over yung K sub B is yung Boltzmann constant and T is yung temperature in Kelvin. So, yung probability kanina, it is dependent on temperature. So, yung temperature natin is related to our thermodynamic beta. Ang thermodynamic beta natin, ito. Yung beta is 1 over Boltzmann constant times temperature. So, ang probability kanina, we can also rewrite it. But, the point here is that yung beta natin and our temperature are inversely proportional to each other. So, na-rewrite na natin yung ating probability in terms of beta instead of yung Boltzmann constant and temperature. So, parang mas simple yung simulation. Usually, ang beta magiging 1 over T na lang kapag iset yung Boltzmann constant as 1. So, ang beta, ayan, are ay inversely proportional to temperature. Sa graphs kanina, nakikita natin na meron tayong beta is equal to 0.1. So, yan yung small na value for beta. At yung beta is equal to 10, yung considered big. So, since it's inversely proportional to temperature again, pwede natin masasabi na yung beta ay may tutuling coldness ng. So, di ba na-concern tayo sa magnetism? So, now we have some consequences sa temperature ng system. So, if aabot yung temperature ng system to be less than the critical temperature, we have ferromagnetic. And kapag, yung on the other hand naman, if greater siya than the critical temperature, then we have paramagnetic, meaning disordered or random yung spins. So, kapag malamig or low temperature, low yung T, gusto ng system na mas maging ordered. So, kumbaga, gusto nilang mag-align. Pero kapag mainit, high temperature, ang mga spin ay parang nagkakagulo, very chaotic. Kasi wala siyang paki sa numbers niya. So, aside from temperature, babalik na tayo ulit sa ating interaction strength J. So, sa ating simulation, pwede natin itong matoggle as positive or negative one. Kasi kanina, positive or negative nga. Pero J can actually be any real number. Tapos, ito ay nakaka-apekto sa cluster preference at alignment. So, if J is positive, we allude to ferromagnetism again. Tapos, yung spins gusto nila mag-align. Kapag negative naman, yung J, negative 1 in this case, anti-ferromagnetism. Spins want to anti-align. Ito ay iba sa paramagnetism kanina na minention kasi may order pa din ang spins kaso, anti-alignment lang. It wasn't as chaotic kanina. However, ang mga anti-ferromagnet ay pwede din maging paramagnetic in high temperature pero hindi ito sa critical temperature na determined kanina. So, yung mga main parameters na we concerned ourselves with, yung temperature at yung interaction strength, yan yung na-highlight sa 4 plots na, yung J at yung thermodynamic beta. Pero may mga other quantities din na dinaderive bilang resulta ng simulation. So, first we have magnetization. So, parang output ito ng system kasi minimeasure niya kung gaano ka-aligned ang spins. Kaya, apektado ito ng temperature at ng interaction strength. So, kapag mas mataas ang M, ibig sabihin, mas aligned sila. Kapag zero, disordered, something like that. Meron din tayong specific heat, C, and susceptibility, Chi. Dito mo makikita kung kailan nagkaroon ng phase transition. So, makikita mo sa plots na mayroong sharp peak around the critical temperature na we will reveal later. So, yung Chi, ganun. Usually malaki siya kapag malapit sa critical temperature. So, gamit ang mga ito, yung mga other properties, pwede natong gawing mga plots, yung magnetization versus temperature, energy versus temperature, etc. Para makita kung paano nagbabago yung system habang umiinit or lumalamig. So, we start with our lattice, meaning, may 50-50 chance na mag-generate ng up or down. Yung up in this case is white kasi positive 1, and then black, yung negative 1 or down. So, this is it in our lattice. As you can see, it looks quite random. Tapos, we keep updating it. So, this is one step. I took one step here. And, but, this doesn't seem as much fun for me. So, piliin na lang natin na mas interactive na simulation para sa inyo. So, fortunately, merong site na parang mas interactive yung simulation. So, pwede mo matatoggle or masaslider dyan yung temperature, yung field, yung sweep skip, kahit yung lattice size, and that's what I'm doing sa video. I was playing around, and then, I think I started with yung critical temperature, yung T sub C, which is, kung saan nag-shift ang system from ordered to disordered. In 2 dimensions, it was determined to be around 2.27. Tapos nilaraan ko ulit yung slider. So, kapag high temperature dito, kita mo, mas mataas na siya kesa sa 2.27. Sobrang random yung makikita natin. Like, parang, yung static sa TV. Yung kakagising mo lang, tapos 3 a.m., tapos on pa pala yung TV. Ganun yung static na maalala ko. So, pag tignan mo yung grid, para kang nanonood ng pixelated image na gumagalaw. And, on the other hand, kapag pinapalamig mo yung system, makikita mo nabubuo yung mga cluster na white or black. So, ang galing sa start ng series na to, parang nag-flip lang tayo ng tiles, tapos nalilito tayo sa neighbors, sa neighborhood, sa pag-ano ng energy, may probability pa. Pero, it turns out na ganun lang talaga kasimple. Like, tapos may nagawa na tayong bonggang-bongga. So, alam mo talagang success ka eh. Bigla kang sumakses eh. But not yet, actually. Anyway, so the point about saying na not yet is because it was just a taste of what you could do, but now we're here to code. So, na-summarize na natin ang behavior ng spins based sa components. Pero how do we code it? Actually, parang mas simple lang nga siya siguro kaysa sa na-discuss sa previous videos kasi tapos na pag-initialize ng lattice at sa paglagay ng Metropolis Hastings algorithm, tapos every few steps i-update lang natin yung grid at image para makita mga patterns. So, ito yung code snippet gamit ang matplotlib. Pwede mo siyang i-plot using image show, so imshow, at mag-set ka ng custom color map like, yung plot.imshow tapos or gray, or you can like choose even a different color scheme. So, kung gusto mo talagang makita yung evolution over time, pwede kang gumamit ng animation. Sa Matplotlib, merong Funk animation from Matplotlib animation. So, with that, pwede kang gumawa ng time-lapse after ilang iterations. So, result is on the next slide. Charan! Nagsimula lang tayo sa pag-flip ng sign ng tiles pero may natutunan na tayong malalim na physics. In learning how magnetism and phase transitions work, parang nag-microdose ka nga ng statistical mechanics a bit. Kasi temperature. So, salamat sa pakikinig. Ito na po yung katapusan ng second iteration of Py-noy. Sana na-inspire kayo to stay curious and therefore yearning to learn. Kita-kits sa next simulation.